Hey everybody, Gianmarc here. Welcome to our second lesson on thermodynamics, and appropriately enough, we'll be talking about the second law of thermodynamics. So you may remember from the music video that the second law of thermodynamics deals with entropy, which is a measure of disorder. If you remember the lyric from the video, it went, "Entropy measures disorder, the universe always wants more." It seems that there's a natural progression that nature seems to favor disorder over order. Or more precisely, we can say that for any group of interacting systems, the overall entropy of all of the systems in any process that they undergo will either stay the same or increase. And they actually only stay the same for something called a reversible process. So most of the time, it will increase. So why does nature favor disorder? Well, hopefully by the end of this discussion, this will seem like the perfectly natural thing to you. So simply put, there's just many more ways for a system to become disordered than there is for it to become ordered. But this is kind of abstract, so again, we're going to go to an example. So let's say one night I'm thinking about thermodynamics, like I do every night, and I get hungry. So I go to the kitchen and I go to the cupboard and I grab a box of cereal, and then I reach for a bowl and I knock the cereal over. And then I look over and the cereal on the counter has just fallen in a random way, but it spells out, "Gianmarc, get out." I'd be freaked out, right? That'd be really scary. Like, how can that happen? And so let's think about that. Why would this freak me out? Well, experience says that this is a highly unlikely thing to happen. But again, why? Why is it unlikely? What makes it unlikely for this to happen? Well, again, if we think about the number of ways that things can happen, there's almost countless different ways for cereal to spill on a counter, but there's only one way to spell my name, right? But you know what, let's get even more specific with this. Let's think of an idealized situation where every spill, anytime we spill cereal, we're going to spill exactly 8 letters out of this, lettered cereal. And let's just assume that they're going to go in a fairly straight line, and we don't care if they're upside down or turned on their side or whatever. Under this simplified case, even with that scenario, there are over 62 billion different ways for 8 letters to fall on the table. 62 billion, think about that. And again, this is an idealized situation where we always spill 8 letters and we've controlled for a bunch of things. So you can see that for it to spell out my name is much less likely than 1 in 62 billion. So that's why it would freak me out. There's just so many ways to spell cereal, but in order for my name to come up, that would be pretty crazy. So again, we're seeing this theme where very few ordered possibilities are getting lost in a sea of disordered possibilities. So the second law states that for any process involving some set of systems, the overall entropy of all the systems will always increase, with the exception of reversible processes, which we're not going to deal with because they are very rare. So the law is pretty clear, but nonetheless, it can actually be kind of easy to mistakenly think that we're seeing entropy decrease for a set of interacting systems. And typically the mistake we make when we think we're seeing this is that we forget to include part of the systems. Take this rock candy, for example. So right here, I have a piece of rock candy, which is actually crystalline sugar. And there's also some food coloring in here, but the structure is due to the sugar. So we have a crystal structure of sugar. But what do I mean by a crystal structure? A crystal structure is when either a set of atoms or molecules stack up in a very organized, repeating pattern. So it would be kind of a lower entropy sort of way of being than having just molecules all over the place randomly. Instead of that, it's a lower entropy thing, right? It's more organized to have them stacked up in a repeating pattern. So to give you a visual for that, let's take a look at these little building block candies. So if we think of these building block candies as being sugar molecules, if they were in a crystal structure, they'd be in a very organized repeating pattern. So just for the sake of example, a brick wall. So right here I'm following the pattern of a brick wall. Every time you know where the next brick is going to be because it follows a repeating pattern. It's very organized and they stack on top of each other, right? But when sugar is dissolved in a solution, well then it can go anywhere it wants, right? And if we think about this, this must be a higher entropy for this sugar. So even thinking on this large macroscopic scale, it still kind of works out. So there's only a few different ways I could have made that wall, right? But I mean, the different ways I can just kind of knock them about and turn them over any direction. I mean, those ways are pretty countless, right? But there's only very specific ways I can stack them in the wall, very less ways. So this is the higher entropy state, and the stacked up way with the wall is the lower entropy state for the sugar molecules. So let's pretend that these rock candy pieces are water molecules, and these are our sugar molecules. So if they were in solution, they're just randomly swishing about in here. They can tumble, they can flip, they can roll all over the place, and they can configure any way they want. But in the factory where they make rock candy, or you can even make it at home, the way it's made is by taking a concentrated solution of sugar dissolved in water and allowing these structures to spontaneously form. So let's think about that. We have a disordered kind of way where our sugar molecules are allowed to just kind of swish about and flow freely within the water in a very disorganized way, and they somehow spontaneously start stacking up into a repeating pattern like this, similar, along the same lines as a brick wall. So why does this spontaneously happen? How can it be that we have this disordered state where sugar molecules can flow freely, they can flip in all sorts of different directions, and then they spontaneously start to stack up in an organized repeating pattern similar to the way bricks do in a brick wall? Why would that spontaneously happen? It seems kind of backwards, right? We're spontaneously gaining order or losing entropy, right? Entropy's gone down for these sugar molecules. Well, I mentioned that the common mistake is that we're not taking something into account. Well, let's think about the water. So there's both water and sugar in our interacting systems here. So let's take into account both the sugar molecules and the water molecules, and also the fact that heat can dissipate in or out of our system, right? Because it's not adiabatic, if you remember that from the first one. So heat can flow in or out of this system. So if our sugar molecules are losing entropy or getting more ordered, what must be happening to the water? That's right, it's getting less ordered. And so entropy is going up for the water. So in fact, what happens in this case, if we have crystals forming, there's actually heat is given off into the water, which makes the water jiggle more vigorously. And that's actually more disordered. And then that heat can then dissipate out of their solution and into the room, the environment, the universe. It can keep going. So what happens is that although we sacrifice some entropy to get this more ordered structure of the crystals, the entropy of the universe has gone up. So how does this disorder elsewhere manifest? How does it happen? Well, if we remember from the previous lesson, I mentioned how we can think of molecules as jiggling, right? This is Richard Feynman's word, jiggling. Molecules, they all jiggle. So if they're jiggling, and then they start stacking up to form these crystal structures, they can't jiggle quite as much, right? If we think of, imagine this thing is jiggly, right? This is a jiggly block, and it can spin, it can flip, go all over the place, and all of a sudden it locks into place in a crystal, right? So when it locks into place like that, that jiggling energy, it had to go somewhere, right? So think back to our hammer example from the previous lesson. When we take a hammer and we bang on a rock, right, we're putting energy, we're doing work, and energy ends up going into the head of the hammer, and we feel it, and we feel some of that energy exit into our hand as heat. So as these jiggling sugar molecules lock into place in this organized way to form these crystal structures, that energy has to dissipate out into the solution. So let's test this out. Now, a sugar crystal takes a really long time to form. So we're going to work with a chemical that crystallizes much more quickly called sodium acetate. So the idea is that we want to show that when this crystal forms, this jiggling energy dissipates outward, and this heat energy dissipating outward causes more disorder in the solution, and then that heat can even dissipate out into the universe and cause more disorder elsewhere. So we'll gain overall disorder by sacrificing some order in the crystal. Wow, that was pretty cool looking, and the temperature did increase pretty considerably. In fact, if you've ever used those reusable chemical hand warmer pouch things, that's actually how they work, is that there's sodium acetate in them, and you initiate crystallization, and as it crystallizes, the heat given off is the heat that goes into your hand and warms your hand up. So if you think about it, heat dissipates out of the crystal into solution into your hand, and that gets the molecules in your hand jiggling more, and the entropy of your hand is increased slightly, right? So you're part of the thermodynamic system yourself.
Actually, the second law of thermodynamics is all about relating the flow of heat between interacting systems and their change in entropy. It can even be used to mathematically prove something that you already know, that if a hot object comes into contact with a colder object, the heat will always flow away from the hotter object and into the colder one. But the main point I want to make sure you understand today is that the second law of thermodynamics tells us that for any set of interacting systems, the total entropy of all the systems will always increase, unless it's a reversible process where the total entropy stays the same. But in practice, it isn't possible to actually build a perfectly reversible system. So as far as nature is concerned, the entropy of the universe is always increasing.
In fact, if we were somehow able to take snapshots of the entire universe, and each snapshot was labeled with the entropy of the whole universe at that moment in time, we would then be able to place those snapshots in order of time by just going with increasing entropy, because the entropy of the universe is always increasing, which is why we call it arrow of time, because it points in the direction of time moving forward is the same thing as entropy increasing. So hopefully you're getting a better feel for entropy and why we should actually expect nature to proceed towards more disorder. So be sure to watch the third lesson on the third law of thermodynamics, where we dive even deeper into the concept of entropy.